Good morning. Last class we have derived Lagrange's equation from Hamilton's principle. Hamilton's principle, as you know, is integral from t1 to t2 t minus v into dt is equal to 0. This is Hamilton's principle, and starting from the Hamilton's principle we have derived the Lagrange's equation, that is d by dt of dou L by dou qj dot minus dou L by dou qj is equal to 0. Now we are going to derive this equation. We are going to derive this equation from another equation, that is we are going to derive Hamilton's principle from D'Alembert's principle. D'Alembert's principle you already know. It is the equation from virtual work done or regarding the virtual displacement. And starting from the D'Alembert's principle, we are going to derive Hamilton's principle. That is, D'Alembert's principle states that sigma I for a system with the n number of particles in which the virtual displacement can be written as Ri, then sigma I is equal to 1 to n Fi, the force acting, external force acting is Fi on ith particle. There are I is equal to 1, 2, 3, 4 etc. particles in a system, and therefore for the total system we can write sigma I is equal to 1 to n Fi minus mi Ri double dot delta Ri is equal to 0. This is D'Alembert's principle. For a system with n number of particles can be represented by position vectors I is equal to 1, 2, 3, 4 etc. and force acting on each particle is F1, F2, F3 etc. and the masses of each particle can be represented as M1, M2, M3 etc. Then D'Alembert's principle can be stated just like this. Now consider this equation. This can be written as equation number 1, and from equation number 1 we can consider the second term. First term is taken as it is. Second term can be taken, that is sigma I is equal to 1 to n mi Ri double dot delta Ri can be written as sigma I is equal to 1 to n d by dt of mi Ri dot delta Ri minus sigma I is equal to 1 to n minus sigma I is equal to 1 to n mi Ri dot d by dt of delta Ri. This is by differentiating u into v. D by dt of uv. Here mi is not a vector. Ri dot and delta Ri are vectors. For d by dt of uv is equal to u into dv by dt plus v into du by dt. In a similar manner, we are differentiating this one. We get this term plus this term. Therefore, the second term of the first equation can be rewritten just like this. We get this equation. Here, we are rearranging one more thing. D by dt of delta Ri. Here, delta and d can be interchanged. Therefore, we can write once again first term as it is. Sigma I is equal to 1 to n d by dt of mi Ri dot delta Ri minus sigma I is equal to 1 to n mi Ri dot last term delta dRi by dt. Delta and d are interchanged, there is no difference. Then d by dt of Ri is equal to Ri dot. Therefore, this can be written as Ri dot. This is the equation number 2. From the first equation we are taking the second part, and from the second equation again we are taking the second term. That is sigma I is equal to 1 to n mi Ri dot delta Ri dot can be written as, you can write just like this, delta sigma I is equal to 1 to n mi Ri dot delta Ri dot. You can write like this, that is mi Ri dot square. Sorry, there is one half also. Mi Ri dot square, differential of mi Ri dot square is equal to mi into Ri dot square, differential of Ri dot square 2 into Ri dot into delta Ri. That 2 can be cancelled by this half. Therefore, this can be replaced. The second term can be replaced by this term. this is equal to delta sigma I is equal to 1 to n half mi Ri dot square. What is half Ri dot square? Half Ri dot square is half mi Vi square. Half mi Vi square is equal to kinetic energy. Therefore, this is equal to sigma I is equal to 1 to n half mi R square is the total kinetic energy, or it is equal to delta T. Therefore, the second term can be replaced by delta T. Now, we can write on the left hand side, the equation is the second part of the first equation. Therefore, the first equation we can substitute in the first equation, right? Sigma I is equal to 1 to n Fi dot delta Ri minus, we can write the second term. Second term is this much. Sigma I is equal to 1 to n d by dt of mi Ri dot delta Ri minus delta T is equal to 0, where I is equal to 1, 2, 3, 4, etc. Now, in this equation, we can take the second term on the right hand side and the remaining terms here itself. That is, sigma I is equal to 1 to n Fi dot delta Ri minus delta T is equal to, this is taken to the right hand side, sigma I is equal to 1 to n d by dt of mi Ri dot delta Ri. Now, this first term can be written as delta of work done. Fi dot delta Ri is the work done, or it can be written as delta V. This is equal to delta V. For the complete particle, delta V minus delta T is equal to delta V minus T is equal to the right hand side. Now, we can integrate the expression from T1 to T2. That is, this term can be taken first. Integral from T1 to T2. Sigma I is equal to 1 to n d by dt of mi Ri dot delta Ri is equal to integral from T1 to T2 delta V minus T with respect to dt we are integrating. Now, integrating the first term, we get, with respect to dt we are integrating, then we get mi Ri dot delta Ri. We get sigma I is equal to 1 to n. We get mi Ri dot delta Ri from T1 to T2. Taking the limits is equal to, on the right hand side, we get delta integral from T1 to T2 V minus T dt. On integrating, giving the limits at T1 and T2, there is no variation for Ri, therefore this term is equal to 0. There is no variation for Ri at the two endpoints, therefore delta V minus T dt is equal to 0, or T minus V dt is equal to integral from T1 to T2 is equal to 0, or delta integral from T1 to T2 L dt is equal to 0. This is the derivation of, this is the expression of Hamilton's principle, which is derived from D'Alembert's principle. Okay. This is the first video. You have to write all the notes now itself, and you have to derive all the things I have given here a lot of times. Then only you can properly derive the equations. And now the second part, we can give some applications of Hamilton's principle, or we can give some applications of Lagrange's equations, that we are giving by another video. Okay.